This video is for the 2018 exam. This one is part A of that test. Okay, number 2. So things that we know 12 kilograms is the mass. We know the speed is 0.25 meters per second. That is speed. This is speed of the cart is tripled, so we have 3 times the speed. The inertia of the cart, we know that inertia is mass and only mass. If I triple the speed, the inertia, being only the mass, is unchanged because inertia is mass. Great. Next question. Okay, starting from rest, we have v initial equals 0. Accelerates to a final speed of 40 meters per second. This is my v final on a runway that is 70 meters long. It goes 70 meters and it wants the magnitude, which means amount, of the acceleration. What is the acceleration? Now, I'm not dropping the jet like a stone, so the acceleration is not 9.81. 9.81 isn't a choice anyway. So I have v initial, I have v final, I have d, and I want acceleration. So with that information there, I can do vf squared is vi squared plus 2ad. Time is not in that equation. I was not given time. It's not asking for time. I do have vf, vi, and d, and I can solve for a. When we work the math, we get that the acceleration is 11 meters per second squared, which is choice 4. All right, next question. 4, we know the mass of a cart, and let's see, 6 kilogram cart, so I know the mass initially traveling at 4 meters per second east, that is v initial, accelerates at 0.5 meters per second squared, that is my acceleration, east, so in east, the same east and east, so the acceleration is in the direction of motion for 3 seconds, so I know the time, and it wants to know what is the speed after, at the end of, so what is v final? And so they want to know what is v final. So I'm not going to need the mass for this because when you look for our equation, now this is very similar. Number 4 is very similar to number 3, except they give us time this time and they don't give us distance. Kind of cram that equation a little bit. That's vf equals vi plus at. I know vi is 4, a is 0.5, and t is 3. And vf is 5.5 meters per second. I just wanted to point out one more time that the acceleration and the velocity, the initial velocity, are in the same direction. So my acceleration is positive if I'm calling my initial velocity positive. If the acceleration were west, I would need to put the acceleration in as negative, and that would affect my answer. That would give me an answer of 2.5 meters per second, which isn't a choice anyway, so then you would have known that you were wrong. Notice 1.5 is an answer choice, which is just AT, so don't forget to add the V initial. Anyway, number 5. So 5 is a projectile question. It gives us an initial velocity of 20 meters per second, and I'm not sure that's going to matter for this problem. I'll note it, V initial is 20 meters per second, but it says, at what angle should the ball be kicked in order for the ball to travel the greatest horizontal distance? So I'm looking to maximize the horizontal distance. We know that for projectiles, 45 degrees is the greatest horizontal distance because that gives the ball or any projectile, it gives it forward speed, but it also gives it upward loft, like upward initial like y velocity, to give it time in the air. 45 degrees maximizes the initial y velocity and the initial x velocity, so you get forward speed and time in the air. You get the best of both worlds, and so 45 degrees on that. All right, next question. Starting from rest, we have a v initial of 0, travels 18 meters. The car goes 18 meters as it accelerates for 3 seconds. That's the time. And what is the acceleration they're asking for? Delta v over t would be nice if I knew vf. I don't. I could maybe go and find vf, but I'm not going to need it. I know D, I know VI, I know T, and I'm looking for A. So I am going to do D is VIT plus 1 half AT squared. I gave myself more room this time so I wouldn't be crunching. VI is 0, so the first part of the expression drops out. And so I wind up with 18 is equal to 3 squared is 9, and half of 9 is 4.5, so I have 18 equals 4.5 times A. I wind up with an acceleration of 4 meters per second squared, and so number 6 is choice 4. Okay, number 7. So we have a ball rolling horizontally and it leaves the tabletop. Already I'm thinking this is horizontal projectile. So if it's horizontal projectile, I probably want to set up a table for projectiles, but let's see what we have. So 3 meters per second rolling horizontally off of a table, so that's initial x velocity, leaves the edge of a tabletop 0.75 meter above the floor. So not only is that a displacement, that is a vertical, that is a y displacement. The ball lands on the floor 0.391 seconds after leaving the tabletop. So the time, what did I just do? There. So the time in the air is 0.391 seconds. That's time. And it says, what is the acceleration? 0.2 seconds after the acceleration, 0.2 seconds after it leaves the, all right, wait a second. So the time in the air is 0.391 seconds. That's the time in the air. It says it lands on the floor. So time in the air. What is the acceleration? 0.2 seconds after it leaves the tabletop. So this is just some random time. It's not going to matter. In fact, I don't even need a table for this problem because it's asking about the acceleration and I'm dealing with a projectile. And we know that for any projectile, I have like it's rolling off of the table with an initial velocity and it arcs down towards the floor at any point in its path. The acceleration for any projectile is g negative 9.81 meters per second squared. And I don't even need to worry about the negative because they say magnitude, which means amount. So it's 9.81 meters per second squared straight down. At all points, any projectile, the acceleration is straight downwards at 9.81 meters per second squared. I didn't even need to make a table to solve or like get an equation or substitute or anything like that. All right, number 8. Projectile, another projectile. Let's go. All right, so this particular question, they are not giving us numbers. They're giving us letters. We know the mass. It says the initial horizontal velocity is Vx. We know Vix. And it's from a height h above level ground. We tell us what the y displacement is. It said which change would have resulted in a greater time of flight for the projectile. Well, we know that for projectiles, time in the air, it depends on the vertical, on y vertical information. And it does not have any relation to mass. So I can get rid of the first one, decreasing mass. No. We are ignoring, this is neglect friction, so we're ignoring air resistance, so mass is not going to have an effect. Now we want to increase, we want the time to increase, more time. So if we want more time, decreasing the height, that's decreasing the y displacement, that's bringing it closer to the ground. That's going to decrease the time in the air, it's bringing it closer to the ground. That is not going to increase the time in the air, so not decreasing the height. Increasing initial horizontal velocity, that is going to increase the horizontal displacement. How far it goes? It is going to send it farther, but it is not going to affect the time because I only care about what happens to the vertical information. So increasing the horizontal velocity is not going to do it. But increasing the height again is the y displacement. If it's thrown from a higher position, it's going to take more time to fall down towards the ground. Increasing the y displacement to 2h would increase the time of flight. To even show you how that works in an equation, if I do d equals vit plus 1 half a t squared, for a horizontal projectile, it says doesn't actually say that it's a horizontal projectile. I think that's what it implies. But we have no initial y velocity, and so by increasing d, we can see that the time also increases. But it also makes sense logically. If you throw something from a higher height, it's going to be in the air for more time. And so 8 is choice 4. Number 9, golf club hits a 0.05 kilogram golf ball with a force of 5,000 newtons. Let's start writing things down. So we know the mass of the golf ball, we know the force on the golf ball, we know the final velocity accelerates up to 44 meters per second. It's stationary, so we know the V initial is 0. So we know V initial, and we know V final, we know the force, we know the mass, and it wants to know what is the impulse imparted to the ball. So impulse is J, and that's the change in momentum, which is caused by the net force on the ball times the time you apply it, which is also equal to, there's another piece of this not on the reference table, and that's m delta v, not on refs. And actually, that's the piece that we're going to use because we know the mass and we know the delta v. We happen to know the force as well, but we don't know the time. So we can't do ft. So I'm going to do J equals m delta v, and I get an impulse of 2.2. Now for this formula, the units are kilogram meters per second, but the equivalent units, because J equals F net T, Newton seconds are equivalent units for impulse. Impulse and momentum have two possible units, kilogram meters per second or Newton seconds. Just be careful. Notice that choice 4 has 2.2 times 10 to the 5, and that is not what we're looking for. We're looking for just straight up 2.2 Newton seconds, and so that's choice 1. All right. Number 10. 10 looks like it's also a impulse question. Let's see what we have. So tennis, racket puts 200 newtons on a ball. Average force exerted on the racket by the ball. So, all right, this is not an impulse question, but let's say what we have. We have force and we have time. And with those two pieces of info, we can calculate the impulse, but they're not asking about the impulse. They're saying what is the force exerted on the racket by the ball. So if whatever Newton's third law, F of A on B, of the racket on the ball, is equal to negative the force of B on A. So the ball hits the racket with as much force. I'll write this down. Newton's third law. The ball hits the racket with as much force as the racket hits the ball. The time does not matter. It's going to be the same. And the motion will not be the same. The acceleration is not the same. The ball accelerates way more than the racket does. I said the force is the same. So the force is going to be the same on both. And so if it's 200 newtons of the racket on the ball, it's 200 newtons of the ball on the racket. 3. All right, that is the first page. Let's take a look at the next page. There are 35 questions in part A. We are not even halfway there. Let's go. Okay, so we have ourselves a ramp question, and it says its box is sliding down the ramp, and it says, which way does friction go? Friction will always oppose motion, so if the velocity is down the ramp, that's the sketchiest arrow I've made in my life. If the velocity is down the ramp, the friction is going to be up the ramp, and so the friction is going to be D, choice 4. Now, keep in mind, the friction is not always up the ramp. If you were pushing something up the ramp and the box were moving up the ramp, then the friction would be B, down the ramp. But in this case, the box is sliding down the ramp, friction opposes motion, and will point upwards. Also, friction is always parallel to the surface, so it would definitely not be A or C. C is the weight. As a matter of fact, let's take a look at what these things represent. C would be the weight going straight down. A is the normal force. Normal force is always perpendicular, and that usually equals the weight when we're not on a ramp. When we are on a ramp, it's equal to weight cosine theta. We call that F perpendicular. And then the portion of the weight going down the ramp, that would be B, although this B vector is actually a little bit long for F parallel, but F parallel, the component of the weight down the ramp, that's going to be equal to Fg weight sine theta. And then going up the ramp would be the friction force, as we said. All right, let's take a look at number 12. It seems that we have a circle question for number 12. It's the only question left in this particular set. So it says, which diagram represents velocity and acceleration? Well, acceleration, the net force, which is equal to the centripetal force, and the acceleration are both always inwards. So that means that 3 is out, 2 is out, 4 is out. That really only leaves us with 1. And then the velocity is going to be perpendicular to the acceleration and tangent to the circle. Keeping in mind this particular circle is clockwise, so the velocity would be upwards. If the circle were counterclockwise, the velocity would be downwards towards the bottom of the page. But just based off the acceleration by itself, for uniform circular motion, the acceleration must point inwards. That gives us choice 1. Okay. Then we have number 13. We have some information. Let's write it down. Okay, so they give us the electric field strength, they give us the force, and they want to know the charge on the particle. This is going to be a calculation. And our formula is E equals F over Q. And I know that because they give me the electric field strength, they give me the force, and they're asking for the charge. When I work the math, I get that the charge is 1.5 times 10 to the negative 6. And in this particular equation, this formula, charge comes out in coulombs. The answers are in coulombs, and so I'll leave it as it is. All right, number 14. Gravitational field strength is what? Well, we should remember that gravitational field strength is the same exact thing as acceleration due to gravity, and the equation for that is G equals weight over mass. And so it says, what is G equal to? Well, I just said that it's weight over mass, and so that is this answer, weight over mass. mg is equal to weight, which is not gravitational field strength, that is weight, so that's not it. G is the universal gravitational constant, that's 6.67 times 10 to the negative 11 Newton meter squared over kilogram squared. That is a thing that's used in this equation, which is also equal to weight. Why am I circling it? It's not the answer. I wanted to highlight it, but it's not the answer. So both 3 and 4 are equal to weight. It's not asking for weight, it's asking for gravitational field strength. And it's not asking for the gravitational constant, it's asking for number 1. Gravitational field strength, which is the same as acceleration due to gravity, is weight per unit mass. So 14 is 1. Okay, so 15, they tell us the energy, which is also work. They tell us the time, and they want to know the power. So of course, to calculate power, I use P equals mv. Psych! That's momentum! I see a bunch of you guys do that. You're like, P is power. Yes, it is. But not lowercase p. It's uppercase P. Don't say P equals mv. Also, what's m and what's v? They gave me energy or work in joules and time in seconds. It's definitely not mv. Power is work over time. So they gave us 2,000 joules of work in 10 seconds. I know that 2,000 divided by 10 is 200. I don't even really need to run that calculation. That's going to be choice 2. Ding. There you go. Next, 16. Attractive or repulsive. But I can tell you right away that the only force that's only attractive only, is gravity. Gravity does not repel. So it can be either or repulsive. Anything that says gravitational, nope, nope, nope. Ding, choice 3. Magnetic and electrostatic. And remember the rule for attraction and repulsion. Opposites attract and likes repel. So positive and negative attract, negative positive attract, positive positive repel, negative negative repel. Same thing for north and south on magnets. North and south attract, south and north attract, north and north repel, south and south repel. You can get the point. Number 17. So they're throwing out some numbers here on number 17, but this is a comparison question. This is a, double, triple, half, whatever. And It's talking about resistivity, and there is only one equation that deals with resistivity, and that's resistance is resistivity times length over cross-sectional area of a wire. And so we have two different wires, and the second wire, the first one has 0.4 meters length, and then the second one has 0.8 meters length. So I'm having twice the length. And I have the same, this is 1 millimeter diameter, 1 millimeter diameter, so it's going to be the same cross-sectional area. And it says copper wire, and then it's copper wire, so that it's going to be the same material, and 0 degrees Celsius, 0 degrees Celsius, same temperature. And I think that's all they tell us. Now, we know that resistivity, rho, depends on the material type and temperature. And we have to be very careful with number 17 because they're asking about the resistivity. We're comparing the resistivity, not the resistance. So if this was resistance that we were talking about, resistance, twice as much length would mean twice as much resistance. And so the answer would be twice as much. Now, thankfully, they did not put twice as much. The resistance of a 0.8 meter length, that's twice the length, so twice the resistance, but twice as much is not an answer. So then you might be like, what happened here? Twice as much is not an answer. They're not asking about resistance, they're asking about resistivity. And resistivity depends on the material type, what it's made out of, and what the temperature is. These two wires are both made out of copper. They're both at 0 degrees Celsius. Yes, I know the resistivity chart refers to room temperature. It doesn't matter. They have the resistivity depends on temperature and material type. They're both made of copper. They're both at freezing, 0 degrees Celsius. And so the resistivity is going to be the same. Choice 3. Again, resistance is double, but that's not a choice. So there you go. 18. One other comment, by the way. They refer to the same diameter. They don't say it's the same cross-sectional area, but cross-sectional area is pi r squared. So with the same diameter, it's the same cross-sectional radius, so it is the same cross-sectional area. 18. Work per unit charge. Per means divide. Work per unit charge is called what? What is that equal to? W over Q is what? W over Q, if you look on page 4 of the reference table, is voltage. Great. That answers that question. So let's find voltage. Voltage is not an answer choice. Great. However, what is potential difference? Also called, aka, voltage. Ding, ding, ding. Choice 4. I just want to say one more time that per means divide. So they're saying work per unit charge. That's work divided by charge. Good for us. That's the second page. Let's go after the next page. I think we are now about halfway done with section A. 19. Man, they're loving the resistivity type questions. So let's take a look at 19. And they're pulling out millivolts. There's a couple things going on here. So things that we know, we say same copper wire. So it's both wires are made out of copper. They're at the same temperature. So same copper wire at the same temperature. So what that tells me is that the resistivity is going to be the same. That's not changing. The length is 2 meters, but it says 2 meter length of copper wire is connected to 24 millivolts. The current is 0.4 amps. That same wire at the same temperature, it's the same wire, so it's going to be the same length as well. So I'm not changing the length, I'm not changing the resistivity, but I am changing, I'm going from 24 millivolts to 48 millivolts. So I just doubled the voltage. And it wants to know, and again, if I have the same resistivity, the same length, it's the same exact wire, I'm not changing anything about the wire, the resistance, R, is rho L over A. If everything about the wire is the same, then it's going to be the same, and same temperature, the same resistance as well. So for the same resistance, if I double the voltage, what happens to the current? If I'm going to double my voltage, that means I'm going to double the current. So if I go from 24 millivolts to 48 millivolts, I go from 0.4 amps to 0.8 amps. I am doubling my current. That is using a very basic equation and a very basic relationship. Ohm's law, R equals V over I. The fact that voltage and current are directly proportional is simple, basic, and important. They threw in a whole bunch of information on this question. Millivolts instead of volts, and they're talking about the different wires and his resistivity involved. They basically took R equals V over I, that relationship, and turned it into a much more complicated question. But I'm telling you, this thing is chock full of details that are distractors. All number 19 is it's just a direct proportion question between voltage and current. That's it. For the same resistance, if you double the voltage, you double the current. And so if the voltage was 0.4 amps when it's 24 millivolts, for the same resistance, if you have twice as much voltage, twice as much current, 0.8. Anyway, 20. Oh goody, let's go for a calculation. We need gravitational force. So wants to know what is the force of gravity, and we are not talking about mg here. We have 2.425 kilogram soccer balls, and the distance between their centers is 0.5 meters. Just a reminder, for the distance between the centers, that is radius. And the reason why that's r radius is because for a lot of these problems, it involves gravity or orbits. And like, for instance, say the Earth and the Moon. And so the distance from the Earth to the Moon from center to center is actually the radius of orbit of the Moon. So that's why they use radius. My point there, do not feel like you have to cut this in half. Don't be like, oh, the distance between them is 0.5 meters, but it's like radius, so I have to like cut it in half because it's actually diameter. No, that 0.5 meters is the actual distance from center to center. 0.5 meters. So you don't have to do anything to that number. You can just leave it alone. You will need to square it in the equation, but you don't need to cut it in half. Speaking of square it in the equation, let's get to work. Universal law of gravitation. This is not a proportional change question, so I will need to include big G from page 1 of the reference tables. All right, there's the work. Now, when we put it in our calcs, I strongly recommend alpha y equals. Incidentally, I don't know what the staying power of this video will be. Alpha y equals is a feature on TI 83 and 84 and maybe other calculators to handle large fractions. And by large, I mean fractions with a bunch of numbers in them. 4.82 times 10 to the negative 11 newtons, and that is choice 2. All right, next question. 21, talking about a sound wave. Sound can travel through water, but not through a vacuum. That is right, because sound is longitudinal. It is a mechanical wave, and it needs a medium. In comparison, a red light wave produced by a laser can travel through both water and a vacuum. The point of this question, so all waves need a medium, but light, when it acts like a particle, does not. And light acts like a wave and a particle all the time. So light can travel through water, but it can also travel through a vacuum, whereas sound cannot travel through vacuum. There's no sound in space. So 21 is 3. All right, 22. So 22, group of soldiers marching across the road. Each soldier steps simultaneously when crossing a bridge. The group does not step simultaneously in order to prevent the bridge from vibrating intensely. What they're hinting at here, and they didn't actually mention, these steps, they're talking about the frequency of how the soldiers step. But the key here, the key point here is the vibrating intensely, that the amplitude of the vibration increases a whole heck of a lot. When the amplitude increases, when all of a sudden, because of the way that the bridge is being disturbed, the amplitude increases a whole heck of a lot, that is a resonance effect. It's not inertia, because inertia is mass, and if anything, inertia is also a resistance to a change in motion. Inertia would resist intense vibrations. If you had a lot of inertia, it resists a change in motion. So inertia wouldn't cause the intense vibrations. And then conservation of momentum is true in collisions, but I don't know if that's going to cause intense vibrations. I could see people saying action and reaction as being a possible answer. I'm not even really going to argue that. Like, I can see why people might say that, but it's the whole point about how all of a sudden the vibrations increase in intensity. And that increase in the amplitude because of the frequency of the steps, that is definitely a resonance effect. Choice 4. I don't like this question because the way they say, oh, how the soldiers are stepping, that's the frequency of their steps and how their feet are hitting the bridge in a particular way. If you don't realize that the feet hitting the bridge in their stepping is representative of the frequency that the bridge is being disturbed, you're not going to see that. I don't like that question. But yeah, 22 is 4. So 23, light wave goes from air into corn oil. What stays the same? Well, the only way frequency can change is through the Doppler effect, not by switching mediums. So said what remains constant? Frequency remains constant. And so let's see. And actually, frequency is in all three, the first three, and even period. Period does stay the same because period is related to frequency. T equals 1 over F. And so period stays the same, frequency stays the same. But I can tell you if you go into corn oil, if I go from air into corn oil, the index of refraction increases and N equals C over V. So if the index goes up, the speed goes down. So if the light wave goes into corn oil, its speed will not stay the same. So speed is not an answer. And the frequency will stay the same, but since V equals F lambda, if the frequency stays the same, but the speed decreases, then the wavelength also needs to decrease as well. And so wavelength does not stay the same, wavelength changes. So not 4, but period and frequency they stay the same. Only way frequency can change is Doppler effect, and so if the frequency doesn't change, neither does the period, because they are literal inverses of each other. And so 23 is 3. All right, 24. Speaking of corn oil and the index of refraction, what is the actual speed there? And so I need to look up the index of refraction. So that frequency, the 5.09 times 10 to the 14 hertz, is the reference frequency for the indices of refraction chart. And so that's where the 1.47 is coming from. That is page 2 of the reference tables. I'll look up the index of refraction for corn oil, and I get 1.47. And so I stick that in for N. I put in 3 times 10 to the 8 meters per second for C. That, of course, is from page 1 of the reference tables, the speed of light in vacuum. And I'm solving for V. And I get 2.04 times 10 to the 8 meters per second. And that is choice 2. All right, 25. Spreading out of a wave after passing through an opening in a barrier, that is definitely diffraction as it spreads out. The picture for diffraction, if I have waves coming through to a barrier, as they pass through the barrier, they change direction, they become semicircles. I messed up this one here. That's a little bit better. So yeah, if they're coming through this way, then they spread out this way, that way. Remember that you get the most diffraction effect when the size of that opening is equal to or less than the wavelength of the waves. All right, so that's 25. All right, 26. 2 times 10 to the negative 11 seconds, and so that's going to be choice 1. T equals 1 over F, that's all there is to it for number 26. Now 27, it's talking about interference. And so what happens when waves, doesn't matter that it's light, when waves interfere with each other. When waves interfere, they affect each other's amplitude. They definitely don't change their speed. The only way frequency can change is Doppler effect. Doppler, relative motion between source and the observer, so the frequency won't change, but there will be a change, the amplitude will change. And so that is 3. I can tell you that max constructive interference when waves are in phase, 0 degrees phase difference, crests meet crests, and troughs meet troughs, you get the maximum increase in amplitude. When there's max destructive interference when crests meet troughs and they're 180 degrees out of phase, you get the maximum decrease in amplitude. All right, 28. All right, so we were talking about glass rod rubbed with silk. A positive charge is given. So how does that work? The protons do not move, so we don't add protons or remove protons. Yes, we're giving a positive charge, but we don't do that by moving the protons because they can't get out of the nucleus. So, and we're giving a positive charge is given, so we're not adding electrons, this is given to the rod. Adding electrons to the rod makes the rod negative. So it says a positive charge is given to the rod. So I don't add electrons to the rod, I remove negatives, electrons, negative particles, negatives. If I take negatives away from a neutral rod, that makes the rod positive. And so 28 is 3. Alrighty, 29. Given energy, solve for the frequency. The formula I'm going to use here is E equals h Planck's constant times F. I have my energy, I have my Planck's constant, I'm going to solve for F. That Planck's constant, of course, is from page 1 of the reference tables. And so I divide both sides by that to get F. And then when I go and get my frequency, it's 2.01 times 10 to the 12 hertz, which is choice 2. Okay, 30, we're going all the way back to kinematics. We have V initial, 11 meters per second, V initial to 19 meters per second, and it doesn't say how much time, to V final, 19 meters per second. It wants the average speed during the interval. I have an initial speed, I have an end speed. I want the average speed. Don't overthink this. If I have initial and final speed and I want the average speed, it's the average of those two numbers. That's it. Next question, 31. Rest mass of the electron. What is the energy in joules? So I can look up the rest mass of an electron from page 1 of the reference tables. It's 9.11 times 10 to the negative 31 kilograms. I want the energy of that, and so that's going to be E equals mc squared. And so we wind up with 8.2 times 10 to the negative 14 joules. Do not forget to square C. And that C, of course, comes from page 1 of the reference tables, the speed of light in vacuum. We are almost there. That is 31 of 35 for part A. So in fact, the next page finishes part A. So let's look at 32, a spring. All right, 32, one spring constant. And it's talking about the force. I know that the force is 10 newtons. And it wants to know spring constant, and I have a stretch. So I'm going to use F equals kx and solve for k. And the x, of course, the spring is stretched to a length of 0.6 meters, so the stretch is 0.6 meters. No, it's not. Read the question carefully. The unstretched length is 0.4 meters. So we start at 0.4 and then we go to a total length of 0.6 meters. And so the actual stretch is the total length minus the original length that it was. And so the actual stretch is 0.2 meters, not 0.6 meters. Be careful. And so we wind up with 10 newtons for the force. We're solving for k. X is 0.2, not 0.6. And so k is going to be 10 divided by 0.2, and that gets us 50 newtons per meter. Read carefully. All right, that was 32, 33. Looks like it's some kind of electricity question. Ooh, this question was on our test this year. But anyway, when the switch is open, there's an electric current in what? Well, there's going to be an electric current wherever there is a loop. So I can see that coming out of the positive, I hit bulb 1, and I come back to the battery. I will definitely get electricity out of bulb 1. So I want to have an answer that includes lamp 1. So it's not choice 2, it's not none. And so it's either 1 or 3. Now 3 says all the lamps are going to be lit. Now that doesn't really make sense because it's an open switch. Why would they have that open switch there? And I can tell you that when I try to close the loop for the other two bulbs, it's like, so coming out of positive, I'm trying to get to, oop, I hit the switch. I hit the open switch. I cannot get to, there's no closed loop from the battery to 2. That is not a thing because the switch is open. Not a thing because the switch is open. And then going to 3, there's the open switch. So I can see, I think I'm hitting undo. I hope I'm not messing up my audio. But yeah, I have a closed loop between the two bulbs here, but that doesn't include a battery. So that's not going to do anything either. And so with that open switch there, I'm not getting a closed loop between the battery and those two bulbs. It's just not happening. I am getting a closed loop between the battery and bulb 1, so lamp 1 only is lighting up for 33. All right, 34, second to last question in part A, represents an electric field. Well, let's go over what an electric field actually shows. So if I were to drop a loose, free-to-move positive test particle into the field, the electric field lines show the path that particle would move. In other words, repelled away from positive and attracted towards negative. So going through here, choice 1 looks pretty good from positive to negative. Choice 2, the shape looks good, but it's going from negative to positive. That's a no. Choice 3, the shape looks good, but it's going in towards positive. That's a no. And choice 4, again, the shape looks good, but it's going out of negative. No. Choice 1 is our answer for 34, going from positive to negative. In fact, all of the shapes, all 4 choices, the shapes are correct. The direction is only correct in the first choice. And then finally 35, we have ourselves a wave, and it says 90 degrees out of phase. That is 1/4 of a wave cycle. Again, to show you what I mean by that. So parts of a wave, we start off with 0, halfway is 180, full is 360, and so 1/4 of the way is 90, and then 3/4 of the way is 270. I can't write 270. 270. Very good. And so 90 is 1/4 of a wave. So what's 1/4 of a wave apart? D and E are actually 90 degrees apart, and so are A and B. But A and B is not a choice. D and E is a choice. So it's D and E. I can tell you that A and E, that's 1, 2, that's 360. Those are actually in phase with each other, A and E. But they're actually 720 degrees out of phase. But, well, not out of phase, but like their phase difference is 720 degrees. But in phase is 0 degrees, 360, 720, etc. B and C are also in phase, and they are a full wave apart. They are 360 degrees apart from each other. C and D are completely out of phase. They're 180 degrees apart, but it's at 90 degrees out of phase, a quarter wave. So 1 and 2, A and E are in phase. They're not out of phase, so not 1. B and C are also in phase. C and D are out of phase, but it's by a half a wave, not 90 degrees. So yeah, D and E are 90 degrees apart, 1/4 of a wave. And that's choice 4. And that is 1 through 35. That is part A of the June 2018 test. That ends this video. And stay tuned for part B from the same test in our next video. Thank you.